Hello all. Here's the code for the StepCounter circuit that I made a couple of weeks ago. Has it been a couple of weeks? Where did all that time go? Okay, so the first thing we have to do is set up the processor, and I'm using a PIC16F84A. So you have to have this line right here in your code, and we have to have this include file. This is hash include PIC16F84.inc, and don't forget the less than and greater than around that word right there. Now you can ignore this right here, and it's probably been fixed since then in the compiler, but it used to be that for the PIC16F84A you'd get an error message, even though there was no error message, and I just always kept it in my code here just, I guess, for anything sentimental value. Next thing we have to do is we have to configure the PIC16F84A. Now we have this semicolon right here, and anything beyond a semicolon is a remark. It's ignored by the compiler. So if you want to put remarks in your code, type in that semicolon and then put your remark. A remark is a very, very powerful tool when you're programming, because in 10 or 20 years when you go to look at this code, you're going to wonder, what in the world was that all about? But if you have a remark, you can say, oh yeah, I remember doing that and why I did it. So the configuration of the PIC16F84 must be done, because for instance down here, these last two bits right here, you have 0, 1. That tells the compiler that I'm going to use an XT oscillator. XT oscillator being a crystal or a clock. There's different versions of oscillators, so you can look at the data sheet for your microcontroller, the PIC16F84A, and find out what to set these bits to. There's RC is one of them, which would be a resistor capacitor oscillator. Up here I've got the watchdog timer disabled, so this bit up here is set to 0. Power up timer enabled. I got this bit right here set to 0. Now here, this is pretty important if you don't want nobody running off with your code. This is your code protection, and if all of these bits right here are set to 0, your code will be protected. When somebody puts your IC on an EEPROM programmer to download your code, it won't download. They'll get all ones instead of the ones and zeros required for the program to run. Now I'm prototyping my hardware, so I'm writing and reading and writing and reading. So I've got all these bits right here set to 1, which is protection disabled. There's something very important here, and this took me a few weeks. I'm exaggerating, of course, but it took me a day or two to figure out. You have 2 underscores right before that word config. It must be 2 underscores. Now let me separate those 2 underscores with the space bar. You see that? That is the underscore, which is on the same key as the minus key on your keyboard. So it's underscore underscore config, and I've got B single quote, the ones and zeros, and ending single quote. This right here indicates that everything following the single and the closed single quote will be in binary. I like to do that. I mean, I could do it in hex. It wouldn't be a problem. But I like to see which bits are set to ones and zeros. Okay, got long-winded on that. Let's go to the next step here. We want to define what these ports mean in a variable. Now, in our code, we could say, for instance, clear file port A, comma 4. That's port A bit 4, and this is port B bit 0. But it makes me have to remember what port A bit 4 is doing and what port B bit 0 is doing. So we have this hash define command right here. So I go hash defined, and I define what port A bit 4 is named in the program. So here I'm calling port A bit 4 the step input. That's the square wave that's going to go into the microcontroller. And I'm calling port B bit 0 the feedback output. That's going to be the emulated Hall effect output. Now, with our port A and port B variable names defined, let's go down here, and we got this next command right here. This is C block. Now every microcontroller is going to be different. What this command does, we have C block and end C in the compiler. And what this does is it sets aside RAM space for a variable that you define. So here in the PIC16F84 in page 1, RAM starts at hex 0C. And I'm placing, whenever this variable step underscore counter is used, it will be used at address 0C hex. Now, if I had another variable under here, let's call it variable A or variable B, the next available memory location would be allocated to that variable A, and the next variable space would be allocated to variable B. So this makes it real easy. In the olden days, you had to say, okay, I want StepCounter to be at address 0C. I want variable A to be at address 0D, and so on. But here, you just drop them in the between C block and NC, and the compiler does all the work for you. Amazing. Okay, we're almost there. Well, no, I take that back. We ain't almost there. Okay, where is your code going to be compiled at? Where is the first memory address that code is going to start at? That's what this origin command does. It says, okay, your code is going to start at 000 hex. 0000 hex. So that's very important. You got to have that in there, or the compiler won't know where to set your code. Now, let me scroll up a little bit. We have to set up the ports, the I/O ports. We have to tell the I/O ports whether they're going to be input or output. For this application, I've only got one input and one output that I'm using, but we have to tell the compiler who the inputs and outputs are. So we move the literal value of 0, little x, 10, that indicates hexadecimal. We move that value of 10 hex to the working register. And then we move the working register to the Tri-State A register. And that tells who the inputs and outputs are for that port. Now, a 0 is an output, and a 1 is an input. And I'm using this bit right here, RA4, that's pin 3, that's our step input. So I'm setting that bit in the tri-state register to 1. And everything else I'm setting as outputs. Why are you setting those as outputs? Well, the reason I'm doing that is because if I set them to inputs, we might have interference enter our microcontroller on those floating pins. So I set them to outputs. Now let me go back. We have to switch. This gets a little bit confusing. When the microcontroller comes up, we're in, I think, bank 0. And we have to switch to bank 1. That's where the Tri-State A and Tri-State B registers are. So this command right here, bank select Tri-State A, tells us that we're switching to the Tri-State A register, which is in bank 1. Whew, confusing. Okay, now what about port B? Port B, we're using RB0. What is that, pin 6? RA4 was on pin 3. RB0 is on pin 6 of the microcontroller, and we're using that as the feedback output, the emulated Hall effect feedback output. So I set all 8 bits of port B to 0. That's 0, 0 hex. So we move the literal to the working register, the literal value being 0, 0 hex, and we move the working register to the Tri-State B file. That's what move LW, move literal to the working register, and move the working register to the file, which is Tri-State B, Tris B. Okay, so now we're going to start running the program. We're all set up. We need to run the program. We have to get back to port A and port B and the status register, which are all in bank 0. So we bank select, the command bank select, port A switches us from bank 1, which was the Tris A and Tris B registers, back to the port A, port B, and status registers, which are in bank 0. Woo! Phew. Okay, now let's look at the first part of the code. What we have to do is we're taking a square wave into this microcontroller, and we want to count those square wave high and lows until we reach the number 50. And then well, let me back up a little bit. I'm getting ahead of myself. The first thing we have to do is we turn on the output, the feedback output. And then we want to count those square waves until we reach the value of 50. And then if we reach the value of 50 steps, we turn the output off, the feedback output off, and then we count another 50 steps. And we reach those other 50 steps, we go and we turn the count output, the feedback output on. And then we count for another 50 steps and continue that process until the machine shut down. So here This is bit clear file. Feedback output. That turns that output off. I'm confusing myself. I'm either on or off or off or on. But anyways, here we are. Bit clear file, feedback output. That would clear that output pin and turn it off. Clear file, CLRF, step counter. This is the counter that we're going to use to count those 50 steps. So here we are. The output is off. The step counter is set to 0. And now we want to see if the step input on pin 3 has gone high. How do we do that? Well, here in the first column is a label. It's called step underscore loop underscore high underscore 1 with a colon at the end of it. Don't forget that colon. Your compiler will crash if you don't see that colon and know that this is a label. Here we drop in and we bit test file skip if set the step input on pin 3. Has it gone high? Well, let's assume that no, it hasn't gone high. This is bit test file, step input is the file, and skip if set. Well, if it hasn't gone high, we drop into this go to, which is step loop high 1, and that go to says, hey, jump back up here. And then we go in here and we test again that step input. Have we gone high? No. Well, let's go back and loop. Have we gone high? No. Go back and loop. Have we gone high? Yes. Bit test file, skip if set. Yes, we've gone high. So we skip the go to and drop down here. And this is step loop low 1. And it says bit test file, skip if clear. We want to check to see if that input, the step input, has gone low. And let's say that we're still high. We drop into this go to, and it says go back to step loop low 1, which is right here. Have we gone low? Nope, we're still high. Well, let's go back. Have we gone high? Have we gone have we gone low? No, not yet, so go back. And here we drop in, hey, we're low. Bit test file, skip if clear. So the step input is low. Now we jump over the go to. We're skipping because we've gone low to here, and this is key. We've looked and we've gone high, and we've looked and we've gone low, and now we want to count that high low as one count. So we increment file step counter comma F. Don't forget that comma F. If you leave that off, it'll put the results in the working register. So we want the increment, the inc file step counter comma F to be like step counter equals step counter plus 1. Now we drop down here and we have to see if we've reached 50 steps. Now here, hex 32, if you converted that to decimal, that's decimal 50. So we move the file step counter, step underscore counter to the working register. And we subtract the literal value of hex 32 from the working register. And in that subtraction, if we had 50 minus 50, the Z flag in the status register would be set. Let me move this over a little bit. And if the Z flag is stepped, we jump past the go to. But if the Z flag is not set, because we're not at the value of hex 32 yet, decimal 50, we go back up to this point right here, and we perform all that same process again. Testing for a high, testing for a low on the step input, pin 3, incrementing the step counter if we've had a high to low transition on that input, testing to see if we're at decimal 50, and if we are, we go to the next step. If not, we go back up here. So let's say we did reach hex value 32 and decimal 50. The Z flag has been set. Bit test file, the file being the Z flag. The Z flag is set, so we skip over this go to, and now we're down here. And previously we had cleared the feedback output, so it was low. Now we set the feedback output so that it is high. Bit set file, feedback output. The feedback output being on pin 6. We have to clear the step counter again because now it's equal to 50. So we don't forget that. You get skewed results if you don't clear the step counter. And again, let me move this over. Again, we want to see if we have a high right here. And when that step input is high, we jump over the go to. We want to see if the step input has gone low. Bit test file skip clear, and if it has, we skip this go to and we increment the step counter. Then we test to see if the step counter is equal to 50, and if it hasn't, we go back to step loop high 2. Now look up here. I had to differentiate. All of this was denoted by that label 1, step loop high 1. But here we're checking for the next 50 steps. The first was the first step of 50 steps, and here we are with the second step of 50. 50 and 50 equal 100 steps. So here we have to have, we're doing exactly the same thing, but we are using 2 at the end. So we've set the output, we've gone low to high on the output, we've cleared the step counter, we're testing for the high. When that square wave in goes high, we go down here and we check to see if we've gone low. When we go low, we increment the step counter. Then we test to see if the step counter equals hex 32 or decimal 50. And when it does, the Z flag is set, and we jump over this go to that takes us back up to here. Now, when this second set of tests has equal 50, we go back to main, which is up here, and we start all over. Shoo-wee. Well, a couple of things about writing this code. You can see that labels are ended by a colon, and they are in the first tab. And operands, bit clear file, bit test file, skip if set. Here's a command go to. These are all in the second tab, the second column. And your operands are in the third column. The compiler needs to see first, second, and third column. And you can stick remarks out here separated by a semicolon at wherever you want. The compiler ignores that, anything beyond that semicolon. And in the very end, in the second column, you have to have the word end. The compiler needs to know where we're done compiling. So, folks, I hope this has been interesting. explanation. Now in the next video I'll put my schematic drawings of this function up. There you go. Hope y'all's having a good day. We're doing alright here. We're doing alright here. We'll see you next time.